Você me avisa, viu, Júlio, quando começar, tá?
Professor, podemos começar já.
Podemos? Okay. So, good morning. Finally arrived this day. Greetings to everyone. We are so happy to start the second CompChem workshop that's part of CapSprint sub-project that's coordinated by Professor José Valquimar and I, with the support of Professor Célia Machado Ronconi, and also the support Professor Wagner Almeida. So I'd like to highlight also and give a special thank to the organizing committee, which has been done an excellent work to have this workshop ready. Without you, dear friends, that would not be possible. So we are so grateful for the Sua Ciência Foundation support and thank all of you participants, wishing a very nice week with great lectures. So let me introduce you the opening lecture that will be given by Professor Julia Contreras-García. Since 2019, we planned to have Professor Julia Contreras-García with us. I invited her in that moment to give the same short course she prepared to the computational chemistry school in Franca, Brazil. Then, I'm so grateful for your acceptance, Julia, to open this event that's special for us since you are reference the woman in science, represent with excellence all the women in science. Professor Julia Contreras-García is senior researcher and team leader of the Laboratoire de Chimie Theorique from Sorbonne University. She developed the NCIPLOT software, which enables visualizations of non-covalent interactions applied to different systems. She's working on supraconductivity and bounding, energy from NCI and machine learning also, density and correlation errors in experimental wave functions. She has more than 10,000 citations, an age index of 32, published papers 93, and is one of the leaders of the Women in Computational Chemistry project, and also member of the European Committee on Chemical Bonding. So it's a great pleasure to have Professor Julia Contreras-García with us, opening this workshop. Please, Professor Julia, the screen is yours. You can talk to us. Thank you.
Thank you very much, Luciano. Can you hear me?
I can.
Okay, that's perfect. Then let me start. And you can see my screen? So I assume that's a yes. So let me start by thanking you, Luciano, for inviting me today. I certainly would have loved to give this course in Brazil, like the first time, but the conditions are certainly not the same. And I'm happy that even in spite of COVID, we are able to go through it and have this course. So what I will be talking about you today, it's somehow half a class, half a scientific presentation, and it deals on non-covalent interactions, and it will be the theoretical basis for the computational lessons that we will be having the rest of the week. So the presentation will be organized as follows. So first of all, I will, there you go. So first of all, I will start by a very brief, hello?
Julia, you need to share your screen to the public.
I am
please.
Sharing.
Yeah.
You don't see it? Okay, let me try again. So you didn't see it up to now?
Not yet.
How about now?
That's good. Now it's okay.
Okay, that's perfect. Thank you. So, okay, you haven't missed much. So here is the outline of what I will be talking about today. So I will start by a brief presentation of what is usually known as the topological approach. And then I'll go into NCI, which stands for Non-Covalent Interaction Index, which is one of these topological approaches used to reveal non-covalent interactions. So I will be giving you both the theory and some applications and walk you through them so that you will get a glimpse of what can be done with NCI in your scientific approaches and what kind of things we will be learning in the coming days during the computational lessons. So, starting with the topological approach. The topological approach, I really like this slide because I think it summarizes in a very visual manner what the topological approach is. So, when you do computational chemistry, quantum chemistry, you start by calculating the wave function of your system. Now, this wave function describes perfectly your system, contains all the information on the ground state, but it is completely delocalized. Let's imagine you are calculating benzene. You will obtain a wave function for benzene as a whole. So you're somehow missing the partition that is in our heads where benzene is formed by carbon and hydrogen, by carbon-carbon bond, carbon-hydrogen bonds. So in order to recover this type of information, what we need to do is some a posteriori treatment, and one of them is the topological approach. So we will choose a chemical function that is derived from the wave function defined in 3D. One of those functions is, for example, the electron density, and we will calculate it in a grid around the molecule. So basically here, for example, you have the benzene molecule I was telling you about. So we will calculate the shape of this function, and we will analyze its shape by means of the things that you've already seen during your high school studies, such as understanding the shape of this function in terms of the maxima, the minima, the saddle points. We will also partition the system into these different regions. As you can see here, for example, we have this chemical function in red, and we can differentiate different regions of the space divided by this function. And we will be able to integrate within those to, for example, obtain charges such as bond charges, bond volumes, and it will all be determined by the meaning of this chemical function. Let's see one example. So we have the oldest way of doing this is known as the atoms in molecules theory. We start again from our benzene molecule. So here we have the isolines around benzene, and very quickly you will be able to tell me where the carbon atoms are, right? So the carbon atoms are here. Those are cusps. They're assimilated to maxima of the function. We can tell that hydrogens are here. So we're able to tell where the atoms are. And now if we actually use the saddle points of the function, so where are the first order saddle points of this function, we can actually locate these red, little red spheres. And these little red spheres, they're used to identify, to characterize bonding. So we have these two types of bonding. So saddle point is equal to a bond. And with this, we can identify the chemical structure. So we can draw our molecule from our wave function. We don't need to know chemistry in advance to know that two carbons at a certain distance will be forming a bond. The question now is, does this happen for every type of bond? And because up to here, we have seen covalent bonds, carbon-hydrogen, carbon-carbon. What I'm going to be focusing on today is non-covalent interactions. Why is that? Now, let's look at this methane molecule. We have carbon-hydrogen covalent bonds. If we analyze a covalent bond, like the one in hydrogen, we will see that we can start from very far away with our hydrogens and start squeezing them together like we do in this potential energy surface. So we will have a very deep energy well, and then it will go up very fast during the repulsion wall. What happens, because this is very deep, is that this actually leads to a very characteristic bonding distance. So we have the hydrogen-hydrogen covalent bond always has this distance or very close to it, because this is mainly, so this dictates the full geometry. This means that these distances are easy to parameterize and they're easy to calculate. Now, what happens if instead of this kind of very deep well, we have something like that? And that's exactly what happens when we have non-covalent bonds. Now we have something that is not deep, it's shallow, and it's very flat, which means that with very different, very small energy differences, we can have a distance of here or here or here or there. So, and this will be affected by all the other atoms around that will be determining where exactly we are in this shallow potential. So basically, the binding energy, well, is shallow. It is less directional. It will be affected by the atoms around it. And it makes it very difficult to parameterize. We will not be able to just tell, okay, let's say a pi-pi interaction is of blah, blah, blah. The range of distances that we will find in real systems is much larger because it will be always affected by the environment. And in many occasions, it's even many atoms involved, like in a pi interaction where we have a benzene ring. So if we go back to this pi interaction I'm talking about, we have the benzene molecule we saw for the atoms in molecules for the electron density analysis. And now we go and analyze with the same system, with the same theory, a dimer where we have a pi-pi stacking in between these two benzenes. Now what we obtain is two bonds in between two pairs of carbon atoms. This is certainly not the image that we have of a pi-pi interaction. Our pi-pi interaction should be all this molecule with all this molecule, or all this pi system with all this pi system. The limitation here comes from the fact that saddle points are always appearing in between two maxima. So we will always have atom pair interactions. So it is difficult for the electron density to identify delocalized interactions. Why is it difficult? I like hiking, so I like using this example. Here we have the profile of these mountains, say the Alps, and we can identify easily, our mind does it automatically, we can identify the different peaks. We can even say there is another one in the background. This is actually looking at these maxima, which are places where the gradient of the height is equal to 0. In our system with the atoms in molecules, we were looking at the same characteristic, which is the density gradient equal to 0. Now, what happens if instead of going to the Alps, we go to the Colorado Canyon? In this case, the profile is extremely flat. It is useless to say that we have a mountain here and here and here and there. It is actually much more useful to say that we have a full profile, a full region where the density gradient is very close to 0. So that is exactly what is happening in our example. Here, for the benzene dimer, all this region is, the density gradient here is all very close to 0. And that also explains the fact that if we actually slipped slightly these two molecules, the critical points will change very fast. But actually, the chemical picture is nearly the same. All this is close to 0. So that's exactly what we will do. We will, instead of just looking at the density gradient equal to 0, like here, we will look at the density gradient going to 0. And that's what NCI does. That's the index we will be looking at today. So the reduced density gradient, it's a non-dimensional quantity based on the density gradient that maximizes the signal for non-covalent interactions. I'm going to show you how. So now, instead of looking at a molecule like we did before with the density, where we just look at these points where the density gradient is 0, we look at all this region where the density gradient is close to 0. How does it work? Let's see, for that, some model densities, because I think it really helps to understand how it works. You should keep in mind that, to a very good approximation, we can understand atomic densities from a sum of exponentials. This is like using a minimal base. So we can express the density of an atom, here we have carbon, as a sum of exponentials, so that if we plot the logarithm, we also actually have straight lines. Since carbon atom has 2 shells, then we have 2 straight lines. And if we fit these lines, then we have a very good approximation to the density in the carbon atom. Now we want to focus on the non-covalent region, so we will want to focus on the tail of the second shell, so that's around here. And when we do that, we can actually calculate the reduced density gradient that I just introduced. For that, we just calculate the density gradient, introduce it in the reduced density gradient formula, and we obtain that actually the reduced density gradient in that region is proportional to rho to the minus 1/3. So if we plot the reduced density gradient in terms of the gradient, we obtain this shape, which is x to the minus 1/3. And so if we care about non-covalent interactions, we want to look at this region, which is low densities. Here you are. And that's where the reduced density gradient goes to infinity. And that can be directly seen from this equation. Now, what happens when, instead of having an atom, we have interactions? When we have an interaction, and if we still use model densities, we will actually, it can also be shown that since we saw atoms can be expressed as a sum of exponentials, molecules can be expressed as a sum of atoms. So we still go through summations. Here we have an example where we have the hydrogen potential energy surface I told you about right before. This is our model. So we have a sum of the 2 hydrogens on minus r halves and r halves. And here you have the results. This distance between the hydrogen atoms is the typical hydrogen-hydrogen distance in solid state in non-covalent interactions. So you see in red the computational result from the wave function, and in green the promolecular result. As you can see here, which is in the middle, in the non-covalent region, the 2 practically overlap. So it's a very good approximation for this region to use this promolecular approach. Now, if we do exactly the same plot that I showed you before, the reduced density gradient, this one, in terms of the density, here you have. So we have the reduced density gradient in terms of the density. Now we still have our rho to the minus 1/3 behavior over here, and that is coming from the tails of the atoms that are not interacting. But we have a new behavior here that comes from the region in between the atoms that are interacting. In this region, it can be shown that S will go to 0. And that's exactly what we see here. So we will have a very differential behavior from the tails that go to infinity to 0, where we have interactions. Let's see how it works for a real example. So here we have formic acid, which we have calculated, and we have plotted the reduced density gradient in terms of the density. As you can see, we have this rho to the minus 1/3 behavior over here. And now if we actually have 2 formic acid together, so we have the dimer, where we expect, for example, here a hydrogen bond, another one here, we have exactly what we expected from the model. We have rho to the minus 1/3 behavior over here in the tails, and we have S going to 0 due to some interactions. So we can actually locate where these interactions are by just plotting the reduced density gradient in real space, meaning we choose an isosurface that cuts these peaks over here, for example, and we plot it. And that's what we get. So we get isosurfaces that represent our non-covalent interactions. So we have the 2 hydrogen bonds, and we have some van der Waals interaction also in between mainly the carbon atoms. I'm telling you now that this is hydrogen bond, this is van der Waals, but how do I know if we want to develop a tool that actually is able to reveal non-covalent interactions and without an a priori knowledge of the chemistry of the system? So we also need a method to differentiate the different interaction types. For that, we are going to use 2 pieces of information. The first one is the electron density itself. If you think about it, let's analyze this example. This is phenol dimer. In phenol dimer, we have the hydrogen bond in between the alcohol groups, the steric repulsion inside the rings, where we have many atoms contributing, and we have van der Waals in between the pi systems. Now, if we plot the reduced density gradient in terms of the density, we obtain 3 peaks, 3 interaction types, 3 peaks. These 2 are equivalent. Which one of those should be each? Well, I cannot tell you about these 2 because they're very similar in strength. But if we have van der Waals, steric repulsion, and hydrogen bond, you can very easily tell me that van der Waals is the weakest one. So it's the one that will appear at lowest densities. So this is going to be van der Waals, and these are the other 2. So we have here steric repulsion and hydrogen bond, and we don't know how to attribute it. If you think about it, these 2 are strong non-covalent interactions, but one is attractive and the other one is repulsive. So we can still find more information about them from the electron density. For that, we just look at the Hessian of the electron density. We diagonalize it. We obtain lambda 1, lambda 2, lambda 3, which actually lead to the Laplacian, which is also very much used in the analysis of chemical bonding. And what is important here is that if we have a bond, or which is a charge accumulation in the perpendicular plane, that means that here at the critical point, we will have lambda 2 smaller than 0. Instead, if we have a steric repulsion, so we have many atoms contributing so that this point is a ring critical point, not a bond critical point, there will be a charge depletion. So lambda 2 will be greater than 0. So we can use this lambda 2 along with the electron density. So we put these 2 pieces of information together. So we use the sign of lambda 2 times the electron density now. So instead of plotting here the electron density, we plot this new value, the sign of lambda 2 times the electron density. And again, here the reduced density gradient. So our initial plot deploys into 2. And now we have on the right density depletion, so repulsion, and on the left density accumulation or bonding interactions. In the middle, we still have van der Waals, where both the density and lambda 2 are very close to 0. We can also use it in the 3D plots that I showed you before, the isosurfaces. So we can color them according to this principle. We usually use blue, green, red coloring. So we use blue for strongly attractive interactions like hydrogen bond, green for very weak like van der Waals, and red for straight clashes. So for example, if we look at a couple of examples that we'll be also looking at in the computational class, we have these results for a hydrogen bond. Hydrogen bonds usually look like this because they're mainly 2 bodies. So it's a hydrogen with the oxygen. We have delocalized interactions, which are flat surfaces. And that now you see, for example, this sudden conformation of benzene dimer where we have, instead of 2, we have 3 bond critical points, but still we have a very similar surface because it all is very flat. And we have here the steric repulsion in bicycle octane, very strong as expected from the textbooks. So where exactly do we spec these NCI signatures? For that, we're going to go towards the next point, which is where are the critical points of NCI? And this can be, in order to understand this, we will start by understanding the physical meaning of NCI. The NCI, the reduced density gradient, is actually related to the bosonic kinetic energy density. So the Weizsäcker kinetic energy density, which is this quantity, is the kinetic energy density of a system where electrons are considered as bosons. So we have the same density as in our system, point-wise, but we assume our electrons are in one orbital. When we do this, just like for those who know the electron localization function, this depends on the electron density. To get rid of this dependence, we divide by the Thomas Fermi gas. So with this, we obtain that this quantity is actually proportional to the reduced density gradient squared. Why is this important? Because actually, this physical meaning avoids the absolute value that we had in the reduced density gradient. And now we can easily take derivatives. We can calculate the gradient of NCI. And we can calculate when it is equal to 0, and that's exactly when the places where we will be getting these surfaces around. So around these points, we will have the surfaces of NCI. We take derivatives, and that's what we obtain. We obtain that the gradient of T-pose is equal to all this. So if we want to make it 0, there are only 2 options. Either we make this equal to 0 or this expression equal to 0. In the first case, density gradient equals to 0. That's exactly what we already saw in atoms in molecules. So basically, what one of the cases in which we are looking at NCI is that we have that we will be recovering all the critical points from atoms in molecules. So we will have surfaces around all of them. And that's what we saw, for example, in the formic acid dimer example I showed you. Note that we will not only be looking at bond critical points, but also at ring and cages. So we will also see the repulsive interactions. And since we're looking at surfaces, not at critical points, we will also be able to tell easily when we have delocalized interactions. Let me show you one example, and we will work through another one during the computational class. So here we have the benzene crystal. In this crystal, we have that there are lots of CH-pi and CHC contacts. We have extracted one of these dimers and analyzed them. So with atoms in molecules, so just the electron density, we have 2 critical points, and we have that these are the following the gradients, we obtain these bond paths. As you can see, in this case, we have a very straight link between the 2. Basically, this hydrogen is very close to this carbon. Instead, this hydrogen over here, H2, is distance to all these other carbons is very similar. So one would expect that this is a CHC and this is a CH-pi. Now, if we look at what the density is giving us, you see that it is also identified just with this carbon atom. We can have a slight intuition that it is actually not only with this carbon, because we don't have a very straight line, but it is like it is having a hard time to decide to which carbon it is going. But if we actually look at this, at NCI, here you have the result for the first case. So for the CHC interaction, you see we have the same disk shape, but in green. So it's a weak interaction because it's an interaction with, it's a hydrogen bond with carbon, a non-conventional hydrogen bond. But still it is very direct. It is very localized. Instead, in the second case, let me show you what happens, this is what you get in the second case. So you have a full interaction of H2 with the pi system. So just from plotting NCI in these delocalized interactions, it is very easy to tell when we have a localized or a non-localized interaction. So basically NCI and bond path or the density nicely match for the localized interaction, but in the case of the delocalized interaction, NCI is very intuitive. In the case of the electron density, we have to start looking at subtle features such as how this bond path is deviating. Now let's look at the second part. We had this part can also be equal to 0. When we make this part equal to 0, we are actually looking at localization in our system. So let's see what happens. This is high. If we look at high densities, we will see that actually the reduced density gradient is giving us the shells in the atoms. So here we have 1 maximum for lithium, we have 2 for sodium, and so on. So the number of atomic shells are correctly predicted on the one side. If we actually go from atoms to molecules, we find Lewis pairs, which is exactly the localization picture we expected. So we have that. Remember, this is a kinetic energy density, and electrons will be slower where they are paired. So this is our TPO, so NCI, and electrons will be slow in the bonds, in the cores, and in the lone pairs. So here you have. So basically, NCI identifies regions of electron localization, be it shell structure, covalent bonds, or lone pairs. What is this interesting for? Well, what I really like this analysis for is for reactivity, because during reactivity, you have bonds forming and breaking. In the transition state, non-covalent interactions usually become much more important. So being able to actually look at broken bonds, forming bonds, and non-covalent interactions, transient non-covalent interactions becomes crucial. And I am going to try to illustrate it with this reaction. So here we have an example where we will have very polarized interactions, covalent interactions over here, rather ionic. And you will also see that a very rich picture of non-covalent interactions appears. So here you have, we start from the H2 molecule, lithium with NH2. And you see here, that's the picture of a very polarized bond. So you see it's not homogeneous, whereas this one is a covalent one. And how here, this non-covalent interaction of the hydrogen that is going to go to the NH2 unit starts becoming stronger and stronger so that the hydrogen is transferred. Now we're getting close to the transition state, and everything is interacting through non-covalent interactions because the covalent ones and ionic ones are weaker in the transition state. And now everything starts going fast again. So the hydrogen has gone to the covalent bond with NH2. The hydrogen goes to lithium. This polarized interaction becomes very weak, and instead we have another polarized covalent bond formed here. The non-covalent interactions, as you can see, become weaker and weaker as we go to the products, very different from what we had during the transition state. And this way we finally arrived to the products. So I think this is a very neat example on how NCI can be used to understand reactivities. I'll show you another one later on. Just let me show you before that NCI is also, this kind of critical points is also very useful for weak densities, for very weak densities, more specifically in the case of intramolecular interactions. So here you have the diol series, intramolecular interactions in butane diol, propane diol, and ethane diol. In all these cases, we have hydrogen bonds in between these alcohol series. And then it is known from the analysis of their stretching that it goes in this direction, strong to moderate to weak. But in all three cases, we do have a hydrogen bond interaction. Now, what happens if we look at the atoms in molecules description? In butanediol, this is the critical point in purple that is representing our hydrogen bond here. And we have the, as I told you, our surface around the critical point. Note that by definition, this is the first type of critical point. So the density gradient is 0, the density of the reduced density gradient is 0, and S is 0. Now, in ethanediol, where we also expect a non-covalent hydrogen bond, we don't have critical points. That's because this structure is too constrained to actually lead to density gradient equal to 0. Nevertheless, the density gradient is very close to 0, so you do get an NCI picture, which is much more stable than just looking at points. We are in the second type of critical point, and in this case, S is not equal to 0. And you can see that from the plots that we were looking at before. In this case, we have the peak related to this interaction is here. S is equal to 0. In the second case, S is not equal to 0. So this is the main difference between the atoms in molecules critical points and the non-atoms in molecules critical points, where we, in both cases, we do get an NCI signal. And we will also be looking at these things during the computational session. Just telling you that the fact that we're looking at these regions, not at just points, makes things much more stable. For example, when we look at this other system, also constrained in SCF, we are getting all the time critical points. In promolecular, for example, we don't. Instead, when we look at NCI, in both cases, we do get an interaction. So NCI is especially advisable when you have a system that where the electron density is very constrained or it changes with the basis set. The last part of the theory I'm going to be telling you about is big systems and integrals. So if you think about it, dispersion and non-covalent interactions in general are critical for many things such as surface chemistry, nanoscale or materials chemistry, biological chemistry for protein folding, ligand receptor binding, and still, how can we can do through solid state calculations. Here we have some packing interactions in self-assembling monolayers, in graphite, the ones I showed you in benzene. But how can we deal with those? We don't have a wave function, so we cannot directly compute the reduced density gradient. Nevertheless, remember that we saw that we can approximate our electron density by promolecular densities, and that it was a pretty good approximation over here, which is the region we're caring about. This means actually also that we don't need a wave function. We just need the atomic coordinates to know where we have to add to place our exponentials. And since it's just summations, this calculation is very fast, so it is applicable to large systems. And let me show you a couple of examples. So here you have a polypeptide. This is an alpha helix with 15 alanine residues. You can see here the hydrogen bonds in between the I and I+4 residues. You also have the van der Waals interactions across and along the helix that stabilize this conformation. It's very different from when you look at the beta sheet. In this case, we have an antiparallel beta sheet with 17 glycine residues. And in this case, what you get is hydrogen bonds in between the different sheets and van der Waals interactions in between the methylenes. Something interesting is that this I'm highlighting here is intermolecular interactions, but we also get intramolecular interactions. And since these densities we're using are additive, we can actually identify each of them. We can say that this intramolecular interaction will be intramolecular because all the density in this region is coming from these atoms over here, which belong to the same fragment. Whereas here, the electron density is coming from the sheets above and below. So we can use this to plot either intermolecular, in this case, for example, only intermolecular interactions. The last example of a big system as for now is this DNA double helix. So you can see how we have the hydrogen bonds in between the cytosine and guanine pair, adenine thymine with 2 hydrogen bonds. We also have the pi stacking along the helix. So everything that would have been expected for a DNA double helix. Now, how to go beyond just looking at these pictures? Since we're saying that we can use promolecular to identify the interactions in these big systems, how about we actually also identify which are the points that are coming from the interaction? So basically, if we get rid of everything that is coming from one fragment only, we will have all the points that belong to the interaction. That's what we have plotted in here. And when we do that, we don't need a reference. So we can do that even for intramolecular interactions, and we can integrate properties. So for example, we can say, what is the charge enclosed in, for example, this NCI region? And when we do that, we did it for a typical benchmark set, which is the S22. You have the points here of the interaction energy versus the integrated density. And you can see that we have an R of 0.94, which is very, very decent for this kind of non-covalent interactions. It is actually not worse than many functionals that are not dispersion corrected. So we have a first peep at these energetics, which means that if we actually have some changes of conformation or an MD trajectory, we will be able to compute it. And that's something we will be seeing it as the last example today. Now, I'm saying we can follow conformational charges. There is one condition here. Remember that these systems are huge. So we need to be able to compute these many times in every time frame. So it needs to be really fast. And for that, we have recently implemented an acceleration, which is actually, it's even somehow a shame that we didn't do it before. So this is, remember the peaks, the neat peaks for small molecules. This all disappears when we go to a big molecule. That's what you get. It's points everywhere because the space is huge. So basically, we're doing this representation, and the only place we care about is this low S, low density region. So what we did is actually to use an adaptative grid. So instead of just doing all the grids over here, we start with a very coarse grid around our molecule and identify the low reduced density gradient, low density region, which is the blue one. And now we just keep computing the space where this was like that and make us a finer grid and identify those places where still the density and S are low. We keep digging and we end up with the fine grid that we need for the plotting and for the interactions, but we didn't have to compute all these fine grids all over here. Doing this for this system, for example, takes us from more than 250 seconds to just 7 in the calculation of our grid quantities, and in total just 14 seconds. So we can use it for example, following MD trajectories, and that's the application I'll show you just in a minute. As I'll be showing you now the several applications pretty fast, so that I don't run over time. So one that I want to show you is how we can use it in mechanistic studies for subtle reactivities. So it is known that chiral recognition is thought to happen, is assumed to happen through the formation of weakly bound complexes, where you have a strong interaction that stabilizes the complex, and the chiral recognition happens somewhere else. And I'm going to show you the example of R-lactate, which is the stable one. So here you have the lactate complex with the OH and NH interactions, which are the important ones. And the stable one is this R-lactate, which actually just means that we have swapped here this CH and H3. So we have this CH3 and H here. And this actually leads to an extra interaction in the lactate, which is a CH pi interaction of this hydrogen with this pi. The interesting thing is that this kind of interaction is about 2 kcal per mole, but there is no direct evidence from the stretchings for this type of interaction. Instead, if we look at the electron density, these shape interactions are very easy to tell. Here you have two examples, benzene, benzene, CH3, benzene, and in all cases, you obtain this kind of cone shape, and that's exactly what we obtain in the R-lactate. So here you have slightly shaped, but basically flat van der Waals surface. Instead, here we have a perfectly formed T-shaped interaction of the H with the benzene group. So in this case, which was in collaboration with experimentalists, NCI enabled us to identify the weak interaction without doubt that was giving rise to chirality. Another example of collaboration with experimentalists is in high pressure. I work a lot in high pressure. Actually, as Luciano was saying, I'm very much involved in women in science, especially the group I'm really involved with is in high pressure. So high pressure means that we need to use small surfaces and something to compress it. So this is a diamond anvil cell. So it's 2 diamonds, and we put the sample inside these two, inside a casket that is going to be compressed by these 2 diamonds. In this case, with our experimental colleagues, they were compressing arsenolite. Arsenolite is this structure which has this arsine oxygen gauges, and then they use a pressure transmitting medium. It's usually helium or silicon oil that they put so that the pressure is transmitted hydrostatically. Now, let me show you the results. So they were trying very different pressure transmitting medium from silicon oil, methyl, ethyl, even no pressure transmitting media, and these are the results, the ones below here. You see that they disappear around here. It's because the sample amorphizes. Instead, you see here we have some points, and that's actually when the helium was used as a pressure transmitting medium. That's pretty astonishing because helium is a noble gas, which means that it's usually a very good pressure transmitting medium because it doesn't interact with the sample. And still here we get completely different results. The sample does not amorphize, and even more, we have over here, if you look at this, the curve is jumping. So something is happening at around 5 GPa. And we did the calculations to know what was happening here, and you have here the results. So when there is no pressure transmitting medium, the mechanical instability was found at around 20 GPa in agreement with experiment. Instead, when we did them with helium as pressure transmitting medium, the helium, which are these blue dots, are going inside the sample because our sample is made by cages with huge van der Waals space in between them. So they're going inside, and they're actually, they must be doing something because the sample does not amorphize anymore. And if we actually look at NCI, you see here these interactions, they're very strong and very localized. So they're going exactly to the places where they stabilize the lone pair repulsion, and they hamper the amorphization of the sample. As a conclusion to this study, we could see that helium actually is usually a very good pressure transmitting medium, but if the sample has voids, it can go inside and interact. So this was a very neat conclusion from these non-covalent interaction studies. And the last one that I'm going to show you today is this beta amyloid fibrin aggregates that are responsible, are thought to be responsible for Alzheimer. So knowing about how they behave is key for the early detection of this disease. So this is an A beta 42 extracted from a fibril structure, and we put it into water, and this is the kind of behavior we had in the molecular dynamics simulation. We went from a parallel beta sheet to an intermolecular beta structure, and then it went to an intramolecular beta hairpin. And remember that we're able to separate intra and intermolecular. So we quantified, we used the integral just for inter and also just for intra, and we plotted it. So here you have the behavior of the intermolecular NCI integral that is maximal around 500 nanoseconds. Let me remind you, that's where you get your intermolecular beta structure. So that's where the intermolecular NCI region, NCI integral points. Instead, when you look at intramolecular, it is maximal at the end, and that's where you obtain your beta hairpin. So we're actually able to track the conformational changes in a semi-quantitative manner along the trajectory. So with this, I'm done. Just telling you that we have now implemented all this in NCIPLOT 4, which has been released, and we're about to release a server so that you can do all these calculations online. You can also download the PDB directly from the protein data bank, clean it, and apply everything I have shown you. So the integration, the adaptative grid, the interpretative tools, and use it through a Wii. And so if I had to give you a summary of my talk today, it would be that non-covalent interactions have a unique signature, and their presence can be revealed from the electron density. You can get different types of interactions from hydrogen bonds, electropropulsion, van der Waals. It is applicable to a wide range of systems. We have seen from small molecules to large, organic, inorganic. We have seen that it can also be used to, that the physical meaning is related to the bosonic behavior, so that we can also reveal the chemical structure. So covalent bonds, intramolecular interactions, so we can follow reactivity, and even we can use it now to quantify and follow conformational changes along trajectories. And these are the people who have been working in these different topics related to NCI along the last years. And with this, I'm really done. Just thank you for your attention, and thank you so much, Luciano, for the invitation, and I will be glad to take your questions.
Julia, we are so, thank you a lot for your talk, very nice talk, and we have here some questions to you. I'm so happy for this presentation, like a lecture to all of us. And I can start here with questions from Rodolfo. Rodolfo has an interesting question here to you. He said, thank you very much. How the basis set affect the quality of the NCIPLOT analysis? Is there any basis set superposition related problem?
Actually, the electron density, it's extremely stable to basis set analysis. Even that was already known from atoms in molecules. It could happen in some extraordinary cases, or like these intramolecular interactions, that results change, the critical points change with the basis set. But I showed you one extreme example where the critical points disappeared, and still we got the NCI signature. So the shape so if you want to go for the quantitative integration, it will change. If you just need to know whether the interaction is there, it is extremely stable. That would be my best answer. For the basis set superposition error, that's exactly something that I am looking at since not so long ago with a colleague who is an expert on basis set superposition error. My assumption is yes, but the effect is so subtle that I think the method will be affecting much more. Let's see.
Okay, thank you. Let's see if you have some other questions here on the YouTube. Let's see here. Just a minute. So we don't have any more, but I have some questions here to you. Julia, as you showed, we can derive the analysis from the quantum chemistry calculations, okay? I could see here a questions from Haroldo that's doing the following questions. If, for example, we need to use the WFN file as an input file for the NCIPLOT, yes, a software from the quantum chemistry calculations. Also, to complement these questions, I'd like to know from you, from the MED simulations, for example, we don't have any electron, okay? And how is the procedure to analyze the trajectory from the MED simulations and analyze the density, yes, along the trajectory, please?
So it's there are two options for calculating NCI. Either you use the wave function, and in that case, you can use the WFN or the WFX files. That's one option. Option number two is to use the promolecular densities I was telling you about, and those are coded inside NCIPLOT. So then you just need the geometry of the system, and the density is approximated. Of course, it will not be as good as the wave function calculation, but as you are saying, when you're looking at an MD calculation and at a trajectory from molecular dynamics from force fields, you will not have the wave function. So having an approximation is already it's good enough to at least understand what's going on. I can't hear you, Luciano.
Oh, okay, sorry. And this is based on the chart from the force field?
No, this is based on our fitting. Remember the carbon atom I showed you?
I remember.
So we did that for all atoms. And so we have the density of every atom fitted inside the code.
Okay, thank you.
There can be a problem if someone wants to use it with a chart, because this is not openly available. This is some developer's version. So if someone wanted to use it with a charged atom, they would have to contact us as for now. Okay, thank you. So let's see here if you have some other questions. Frederico Henrique, please, asked, very nice presentation. How would you use NCI analysis to follow the steps? Yes, it is on the screen now. Very nice presentations. How would you use NCI analysis to follow the steps? Yes, in MED calculations when the focus is to identify non-covalent interactions between species and especially for the biomolecule system. So that's like the example I showed. You can follow, you can actually use, like I did, you can also choose to only analyze it between certain residues, because think that these densities, you can choose which ones you're taking because everything is additive. So you can choose if you just want to analyze a given interaction and how it evolves, only intermolecular or only intramolecular. So there are many different things you can choose to follow during your trajectory. Okay, thank you. I have another question, interesting question here from the Gunnar Mota. Gunnar Mota asked, has bosonic behavior correlation with Bose-Einstein statistical analysis or properties? Not much. Because we're still, it's local, it's a point-wise use. The density is coming from a fermionic system. Yeah. And not a bosonic system, yes. So it's a reference, it's just like we do in DFT. It's a non-existing reference.
Yeah, okay. So thank you. Just see here if we have another questions to you, please. Okay. Okay, if we don't have any questions, I can maybe do a last one, okay?
Sure.
You showed that pathway for a reaction, showing the
Yes.
changing on the electron density along the pathway, okay? That was nice, very interesting, because we can exactly see this pathway and the reaction occurring along the analysis. I believe for that you are using a kind of scan analysis, scan calculations
Yep.
from QM, yes?
Yes.
Using the ab initio molecular dynamics, it's also possible to
Yep.
analyze this pathway from the NCI software.
Yeah, absolutely.
And also we need to save the WFN input file along the simulations.
Yep.
And I have a curiosity. It's possible to cope NCI software together with the ab initio MD simulation software, like you know what I mean?
We developed, yeah,
Along.
we used a script that, I mean, if you like, if you want, we can share it. We can
Okay,
also
nice.
upload it. Yeah, it's we did it for a couple of examples. So we have I think we never uploaded it, but I can upload it to the webpage, and if you want it, I can certainly send it.
Yeah, nice. Thank you. Good. So, thank you, Professor Julia Contreras-García. She will be with us, especially for the subscribers that are included in the practical workshop on Tuesday, Wednesday, and Thursday morning.
Mm.
I'd like to thank you again for this very interesting talk. Uh, we're gonna have the afternoon session at 2 p.m. Hope to see you soon. Thank you. Bye bye.
Thank you very much, Luciano. Hopefully next time in Brazil.
I hope so.
Bye bye. Thank you very much, everyone.